Imagine a future where Earth is bathed in clean, renewable energy 24 hours a day, 7 days a week. This isn't science fiction, but a potential reality with solar power satellites. These orbiting power plants could capture sunlight continuously, unaffected by weather or the Earth's rotation. Unlike ground-based solar panels, which are limited by daylight hours and atmospheric interference, space-based solar power offers a consistent and abundant source of energy. The sun, a giant fusion reactor in space, showers our planet with more energy in an hour than we consume in a year. Solar power satellites could be the key to unlocking this vast, untapped resource. This technology holds the promise of meeting the world's growing energy needs while significantly reducing our reliance on fossil fuels. It's a bold vision, but one that's becoming increasingly viable thanks to technological advancements in areas such as robotics, materials, science, and reusable rockets. The journey from concept to reality won't be easy, but the potential rewards are simply too great to ignore. The pursuit of space-based solar power is a testament to human ingenuity, a bold step towards securing a sustainable future for generations to come. The concept behind solar power satellites, while ambitious, is surprisingly straightforward. Imagine a satellite positioned in geosynchronous orbit, approximately 22,000 miles above Earth. This strategic positioning allows the satellite to remain stationary relative to a fixed point on the ground, ensuring constant sunlight exposure. Massive arrays of solar panels, spread out like shimmering wings, capture the sun's energy, converting it into electricity. However, transmitting this energy back to Earth requires an ingenious solution: microwaves. The electricity generated by the solar panels is used to power microwave generators on the satellite. These generators produce a focused beam of microwaves, a form of electromagnetic radiation, which is directed towards a receiving station on Earth. This station, known as a rectenna, is essentially a giant antenna designed specifically to capture microwave energy. The rectenna then converts the microwaves back into electricity, which can be fed into the existing power grid. Solar power satellites offer several key advantages over traditional Earth-based solar panels. The most obvious advantage is their uninterrupted access to sunlight. Unlike ground-based panels, which are subject to day-night cycles and weather patterns, satellites in space can bask in the sun's rays 24/7. This continuous energy harvesting translates to significantly higher energy yields, making space-based solar a potentially more efficient power source. Furthermore, the Earth's atmosphere absorbs and scatters a significant portion of sunlight, reducing the efficiency of ground-based solar panels. Solar power satellites, positioned above the atmosphere, bypass this limitation entirely, capturing the full spectrum of solar energy. This means that for the same surface area, a solar power satellite can generate significantly more power than a ground-based solar farm. Additionally, space-based solar eliminates the need for vast tracts of land required for large-scale solar farms, preserving valuable land for other uses. The energy generation potential of a single solar power satellite is staggering. While the exact output can vary depending on the size and design of the satellite, even a modestly sized satellite could generate gigawatts of power, enough to power millions of homes. To put this into perspective, a single, large-scale solar power satellite could potentially generate as much electricity as a conventional power plant, but without the carbon emissions. This immense power generation capacity makes space-based solar an attractive solution for meeting the ever-increasing global energy demand. As the world's population grows and developing nations industrialize, the need for clean, reliable energy will only become more critical. Solar power satellites offer a scalable and sustainable energy solution, capable of meeting the needs of billions. Section 5. Costs and Challenges. A look at the financial and technological landscape. Despite its immense potential, space-based solar power is not without its challenges. The most significant hurdle is the cost. Launching and assembling massive structures in space is an incredibly expensive undertaking, even with recent advancements in reusable rocket technology. The development, construction, and deployment of a single solar power satellite would require a substantial financial investment, potentially billions if not trillions of dollars. However, it's important to consider the long-term economic benefits. Once operational, a solar power satellite could provide clean energy for decades, with minimal operating costs compared to traditional power plants. Moreover, the cost of space-based solar is expected to decrease significantly in the coming years as technologies mature and economies of scale come into play. Section 6. Material Marvels. The quest for lighter, more efficient solar cells. Advancements in materials. Science are crucial for making solar power satellites a reality. Traditional silicon-based solar panels are heavy and bulky, making them expensive to launch into space. Researchers are actively developing new generations of solar cells that are lighter, more efficient, and more durable, capable of withstanding the harsh conditions of space. These next-generation solar cells, often made from thin films or advanced materials like perovskites, offer higher energy conversion rates while significantly reducing the overall weight of the solar arrays. This reduction in mass translates directly into lower launch costs, making space-based solar more economically viable. Section 7. Robotics. The unsung heroes of space-based construction. Assembling massive structures in space presents a unique set of challenges. Traditional methods of human spaceflight are simply too risky and expensive for large-scale construction projects. This is where robotics comes into play. Advanced robots, capable of operating autonomously or with minimal human intervention, will be essential for assembling and maintaining solar power satellites. These robotic systems, equipped with artificial intelligence and advanced sensors, can work tirelessly in the harsh environment of space, performing tasks with precision and efficiency. From welding and fastening to inspection and repair, robots will play a pivotal role in making space-based solar a reality. Section 8. Starship to the rescue. Reusable rockets revolutionizing space access. The cost of launching payloads into space has long been a major obstacle for space exploration and development. However, the emergence of reusable rockets such as SpaceX's Starship is poised to revolutionize space access, making it significantly more affordable to transport materials and equipment into orbit. Starship, designed to be fully reusable, can transport over 100 metric tons to low Earth orbit, and potentially even more to higher orbits with refueling. This capability opens up unprecedented possibilities for space-based infrastructure projects, including the construction and deployment of solar power satellites. Section 9. A global energy revolution. The transformative power of space-based solar. The successful deployment of solar power satellites could have a truly transformative impact on the global energy landscape. Imagine a world where clean, renewable energy is available to everyone, regardless of geographic location or economic status. Space-based solar has the potential to electrify remote communities, power disaster relief efforts, and fuel economic development in developing nations. Furthermore, by reducing our reliance on fossil fuels, space-based solar could play a crucial role in mitigating climate change. It's a bold vision, but one that could pave the way for a more sustainable and equitable future for all. Section 10. Environmental impact. A greener future, powered by the sun. While space-based solar power offers a cleaner alternative to fossil fuels, it's essential to consider its potential environmental impacts. Launching rockets into space does produce emissions, and the manufacturing of solar cells and other components requires energy and resources. However, life cycle analyses suggest that the overall environmental footprint of space-based solar is significantly lower than that of fossil fuels. Moreover, advancements in rocket technology, such as the use of cleaner fuels and reusable rockets, are continuously reducing the environmental impact of space launches. Section 11. Conclusion. Reaching for the stars, powering our future. Solar power satellites represent a bold and ambitious vision for the future of energy. While significant challenges remain, the potential benefits of this technology are simply too great to ignore. As we continue to push the boundaries of space exploration and technological innovation, space-based solar power could very well become a key pillar in our quest for a sustainable and energy-abundant future. It's a future worth striving for, a future where we harness the power of the stars to illuminate our homes, fuel our industries, and protect our planet for generations to come.